In this video I'm going to make this microcontroller talk to my desktop computer, and what it says is going to show up on this display here. And the way I'm going to do that is by connecting two of the pins from my microcontroller to a separate USB-to-UART card that's going to be connected to the USB port on my computer. More specifically, I'm going to write a UART driver, and my end goal is to be able to write a single line of code to print a string to the terminal. And printing strings or logs to a terminal is another one of those things that are nice to get set up early in an embedded project, because similar to having asserts and being able to blink an LED, it's another one of those debug facilities that are nice to have during development. I'm going to divide the implementation into two videos. So in this video I'm going to focus on the lower parts. So in this video I'm going to implement the UART driver. That is the code that's going to write to the registers related to the UART peripheral. And this driver will be able to write a single character to the terminal. And then in the next video I'm going to implement the printf function that's going to be able to print formatted strings to the terminal. Further on in this video I'm going to divide the UART driver implementation into two stages. So first of all, I'm going to implement a simple driver that's going to rely on polling. So it's simply going to write a byte to a register and then poll a register to wait until the byte has been written. And then in the second stage, I'm going to make this more efficient by making it interrupt driven and implement a simple ring buffer. As usual in this video series, I will be doing the implementation using this development board, or the microcontroller on this development board, which is the same microcontroller as I have on this robot, which is the project that I'm programming in this video series. But as I've said before, I'm doing these first couple of videos on the launchpad to make the videos more isolated, and then in a later video I will move on to program on the actual robot. But even so, what I'm doing here, or the general approach that I'm trying to demonstrate here, is really going to apply to any microcontroller. So my aim is for you to find this video useful even if you're not programming this particular microcontroller. Before we jump straight into the implementation, I would like to first talk a bit about what UART is. First of all, UART is technically not a protocol similar to I2C and SPI. It's actually a device, and UART stands for Universal Asynchronous Receiver Transceiver, and it's a hardware device that's going to, in this case, be integrated into the microcontroller. And it's a device that takes parallel data as input and outputs serial data bit by bit. And so in practice, the CPU is typically going to write a byte of data to a register, and then the UART device is going to shift out the bits, the individual bits of the byte serially, one by one, out on the transmission line. And the UART is quite simple. It only has two lines. So one line for receiving data and one line for sending data. So transmit and receive. And UART is universal because it can be configured to implement several different serial protocols. And it's asynchronous because it doesn't have a dedicated clock line. So that means that for two UART devices to be able to communicate with each other, they need to have the same serial protocol configured. And they must also roughly be configured to have the same clock speed or clock rate, also called the baud rate. It doesn't have to be exactly the same. It has to be within 5 or 10% for it to work. So there is some leeway. And apart from this, for two devices to be able to communicate with each other, they must also support the same electrical standard. And this standard is going to be implemented by a separate hardware chip or hardware circuit, usually called a line driver. So that's going to be sitting basically in front of the UART device. And this line driver has to implement the same standard on both ends for this to work, because this standard determines the electrical interface. So the line driver takes the logic input and output from the UART and translate that to electrical voltages on the output. There are different standards that these line drivers can implement, but the most common one, and the one that's on inside my microcontroller, is the RS-232 standard. So it's just important to make sure that when you connect two UART devices with each other, that they support the same RS standard. It's really not something you're going to notice as a programmer, because that's also going to be integrated into the microcontroller. But it's good to be aware of. So for clarity, I can just add it in here inside my microcontroller. Like that. These days, when you want to send strings of data from your microcontroller to display on your computer, UART has become the de facto standard way to do that. But technically, you could also do this with I2C and SPI. But there are several reasons for why we're doing this using UART instead of other communication interfaces. The first reason is historical. Simply speaking, UART has been around for a long time, so it has just naturally become the standard way to do this. First mover advantage, so to speak. A second reason is design intention. UART was originally designed for connecting teletypewriters to the early computers, so it was actually designed to transfer characters serially to a terminal, which is in contrast to communication interfaces like SPI and I2C, which were originally designed to connect different ICs. A third reason is availability. UART is simple to implement in hardware, and as such it's available in most microcontrollers, and even if it's not, it's easy to implement in software through bit banging. Overall, I just shortly wanted to mention this here, because I think sometimes it can be good to reflect on why we do things a certain way and not just only take it for granted. Another thing I should mention before I get into the code is that a problem with modern computers when it comes to UART is that we can no longer connect our UART devices directly to our computer, because our modern computers no longer have dedicated RS-232 ports, COM ports, because these have been phased out in favor of USB ports. And for this reason, to connect this microcontroller to my computer, I need to have a separate chip, a converter chip, or a so-called USB-to-UART bridge that translates the traffic from the UART to USB. And this chip is going to have associated or a corresponding driver on, in this case, on Linux, that's going to show up as a serial device that I can talk to. In this case, it's not strictly necessary for me to have this separate chip, since on this development board it actually have a separate USB-to-UART chip on it. But since it's limited in terms of how high baud rate it can use, it only goes up to 9600, because it has been pre-configured that way by TI, and I don't think there is an easy way to change it. And for this reason, I'm going with this separate board instead. Also, on the actual robot, I don't have a dedicated chip like this on the board. But anyway, this chip is quite simple. I just need to connect TX, RX and ground, and then the USB on the other end. So now I'm going to implement the first stage of the implementation in this video, which means that I'm going to create the polling-based solution that essentially configures the UART peripheral and writes to the transmit buffer to send out a single character to the terminal. And the UART peripheral on my microcontroller, as with any other microcontroller, is documented in the datasheet. So when I'm configuring a peripheral like this, I will refer to the datasheet to understand which registers and so on that I need to write to. If you're trying to set up UART on a different microcontroller, you would have to refer to another datasheet, obviously. Okay, so in the datasheet of the MSP430, there is an overview of the UART module. So there is like a bunch of registers and blocks here. But what I'm mostly interested in is going to be the transmit part of this module, because I'm not going to configure the UART peripheral to receive any bytes. I'm just going to send bytes out to the terminal. So I'm not going to accept any data from the terminal. And as such, what I'm going to need to configure is going to be, well, first of all, I need to select the input clock source that I want to use. And in this case, I will be using the subsystem clock, which I set to 16 megahertz in the last video. And then I also need to configure this block here, the baud rate generator, to generate the desired baud rate from the input clock rate. So I need to set the prescaler as well as the modulator here to get the correct baud rate from the input clock. And I'm going for a baud rate of 115,200, which is a fairly common baud rate for UART communication. And it's going to be more than enough for the use case here, which is to send strings to a terminal. And once I've configured the baud rate and selected the input clock source, that's pretty much all I have to do, because I'm going to go for the default configuration of the UART module. And this means that for every byte I'm sending, there's going to be, like always when you send a byte with UART, there is going to be a start bit. And then as for the data, there's going to be 8 data bits by default, so a single byte. So let's just use an example number. And then there is I'm not going to have any parity bit and just a single stop bit. And what these bits do, first of all, the start bit, as the name suggests, marks the start of the message, and the data bits contains the data. And a parity bit can be used to make the communication more reliable, because when you're communicating over an electrical line, there's always going to be some sources of errors, so there's always the risk of getting a bit error, and the parity bit can be used to detect that. And finally, the stop bit is used to mark the end of the message, and you can configure to have several stop bits, and similar to the parity bit, several stop bits can also help with making the communication more reliable. But overall, I found that this configuration works for my use case, and I haven't noticed any transmission errors, and it wouldn't be the end of the world for me to have a few transmission errors, because sending traces to a terminal is not really a critical function. So 1 start bit, 8 data bits, no parity bit, and 1 stop bit is the default configuration of the UART peripheral on my microcontroller. Okay, so let's now jump into the IDE and set up a new project. I will implement everything inside the IDE from an empty project and make sure that it works there before I move it to the rest of my project code, because I think it will be easier for you to understand what I'm doing here if you're not distracted by the rest of the project code of this robot. So I'm just going to create a new project using the GCC compiler, and I'm just going to call it the UART driver. Okay, so before I write the UART driver, I first must do a couple of things right after the microcontroller boots up, which I already do in my main project. So first of all, I will put this in a separate function called MCU init. I have a similar function inside my main project. And here I must make sure that I first of all configure the clock rate of the microcontroller. Because by default, as I mentioned in the last video, it's running at 1 megahertz and I want to run it at 16 megahertz. So I have to write the 2 registers here to make sure that the clock source that I will input into the UART peripheral runs at 16 megahertz. And I'm also going to move the stopping of the watchdog into this function. And then I will call this at top of main. And I also need to configure the 2 IO pins that are allocated for the UART peripheral, the transmit and receive pin, where actually I don't need to set the receive pin since I'm just going to be transmitting, but I will configure the receive pin anyway. And I need to explicitly set this for UART because the IO pins, as I've explained before, can be used for multiple functions, and you have to explicitly write to a register to mux them to the right peripheral. And in this case, it's enough for me to just write to the select register of port 1. And then I should call this from my MCU init function. And then I can create a separate file to hold the UART driver that I'm going to implement. So I'm going to have a header called uart.h and a header and an implementation file called uart.c. And then I'm just going to edit this file a bit according to my styling. So remove the underscore, change the comment style, doesn't really matter, but I have my preferences. And here I'm first of all going to have a function to initialize the peripheral. So this function will be the one setting up the peripheral. And then I'm going to have a function to send a single character, and I'm going to call that UART put char. And I'm also going to suffix that with polling because as I said before, I'm going to implement this driver in 2 stages. In the first stage, I'm going to solve things by polling, and then in the next stage I will improve on this by using interrupts instead. And this function is going to just take a character, so car C, like that, and I can make sure that I include this in my main file. So that's going to be include UART.a. And then we can go ahead and implement these functions, starting with UART init. This should also include UART.h. The first thing I'm going to do in this function is to have an assert, which I'm not going to implement now, but I will implement that, or I will add that when I move this to my actual project. So this is going to make sure that this function has not already been called. And then what you need to do when you initialize the UART is explained inside the datasheet. So these are the steps. And what they're saying here is that first you should set the UART module in reset. And then once you have set in reset, it will stay in reset because it should be in reset while you configure it. And then you initialize or configure the registers that you need to set to configure the peripheral as you want it to be configured. And here they recommend that you also configure the ports at this stage. I don't think that's necessary, but maybe it's good practice to do it, but I'm not going to do that. And then once you're done with the configuration, you clear this bit to leave the reset condition, and then the UART peripheral is ready to operate. So I'm just going to follow what they said. So I begin by putting the module into reset. And I also like to add a clarifying comment on why I do this. Just in general, I think it's nice to just put some comments next to the register rights to make it more clear when you're reading the code, so you don't always have to refer to the datasheet and you can just read the code to understand what's going on. And here I'm going to configure it, and then I need to clear reset to leave the reset condition like that. And then I have to write this register to set the parity bit and the number of stop bits and the length of the data bit. But as I said before, I'm going to use the default configuration, so I don't actually need to write to this register, but I'm going to write 0 to it just to make this more clear. And similarly for this write, I leave a comment on top just to explain what I'm doing to make it more clear. So, and the next thing I'm going to do is select the clock source, and I'm going to select the subsystem clock as the clock source, which thanks to this configuration is going to clock at 16 megahertz like this. And once again, to know what I need to set these registers to, I just refer to the datasheet. And then one thing that is a bit more complicated on this peripheral is how you configure the baud rate. Because the peripheral can take different clock sources and different clock frequencies as input and also generate different baud rates. And this means that you have to do some calculations to get the appropriate data you need to write to the corresponding registers. The user guide for the microcontroller actually has a table with some common values to make this a bit easier. So down here is a table of values, so it gives the values you need to write to the corresponding registers. But for clarity, I'm actually going to not just pick the values from this table and instead calculate the value, which may be a bit cryptic the first time you read a datasheet like this, but it's actually not that difficult. And by the way, always when you are going to configure a new peripheral for a microcontroller you're not familiar with, you should read through the datasheet, the entire chapter explaining the peripheral, because it can be so easy to overlook an important step. So that's just a recommendation in general. Read the datasheet. Okay, so for the baud rate, there are 2 different baud rate modes you can use. One is called low frequency and one is called oversampling. And the difference between these two, as far as I understand, is that in the oversampling mode you sample more often, which means that you should reduce the probability of errors. But in my case, I found it to work fine with the low frequency mode, so that's what I'm going for. But if you were to use the oversampling mode, you would have to do the calculation a bit differently, or at least use different values, but it's going to be similar overall. Okay, so when we set the baud rate mode, the first thing we need to do is to calculate this number, n, which is the divisor, and that's the division between the input clock, so in my case 16 megahertz, over the baud rate, which is going to be 115,000 in my case. So in my code, I'm going to do these calculations in defines. So first I define the clock rate of the subsystem clock, just so that I have a number for it here. And then I just have another define here, since in the datasheet the input clock to the UART peripheral is called BR clock, so this just makes that a bit more clear. And then I have a define for my desired baud rate, which is this much. And as I said before, this is a common baud rate to use for UART. And then to calculate the number n, or the divisor, I just divide the clock rate with the baud rate. And I also cast this to float, so that it's a fractional number. Because the next thing I have to do is to extract the fractional part and the integer part. So first I have to extract the integer part, which is just going to be a matter of casting this to an integer, like that. And just for good practice, I can sanity check that this division, or that the result of this division actually fits inside a 16-bit integer. And I can do that by adding a static assert, like that. So this is the max value for a 16-bit integer, since this will translate to 16 ones if you think in binary. Another thing they mention in the datasheet is that the maximum baud rate can't be larger than 1/3 of the source clock frequency. So I can also add another static assert to ensure that it isn't. I already know that it's not, and I'm not going to change these values, but I think it's always nice to add a static assert whenever you can. And it also kind of serves as documentation in this case. So I've extracted the integer part of this division here, and now I'm going to extract the fractional part of it. And that's quite easy. I can just subtract the divisor with the integer that I just extracted. Because, for example, let's say the division ended up being 135.77. That would make the integer int 135, and so the divisor would be this. And then to get the fractional part, I can just subtract the divisor with the integer and get 0.77. And the next thing I need to do is calculate the value I need to put inside this register, which controls the modulator, which is this part. This one is going to control this part. So the fractional part controls the modulator, and the integer part controls the prescaler. So basically, setting the prescaler gives you a baud rate approximately similar to the baud rate you desire. But the modulator makes it even more exact. So if the clock rate is not evenly divisible by the baud rate, you need the modulator to ensure that you get a baud rate that's closer to the baud rate that you desire. And the way you calculate the modulator number is by taking the fractional part, the part that I just calculated, and multiply that with 8. And then you have to round that down, but I can just cast it to an integer. That would do the same in this case. So multiply the fractional part that I just extracted with 8, and then casting it to an integer. And then I add another static assert here to ensure that this value is below 8, since I know that this value should fit within a 3-bit number, so it can't be larger than 7. And by the way, for the integer part, since the registers that you write to on the MSP430, maybe not all of the registers, but at least the registers related to the UART peripheral, all of them are 8 bits, and this means that this is going to be divided across 2 registers. So I need to divide this into a high byte and a low byte, which I can do by masking the lower part to get the low byte, and then shifting to get the higher byte. So then I set the prescaler to the integer part of the divisor by writing to these 2 registers. So the first one takes the low byte and the second one takes the high byte. So that sets the prescaler. And next I need to set the modulation, and then I have to write to this register. And if we take a look at the datasheet, at the values this register takes, this register is divided into 3 sections. So this section, or the 4 most significant bits, sets the first modulation stage, and this is actually only used when you're using enabling oversampling, which I haven't enabled since I'm using the low frequency mode, so I can ignore these bits. And the oversampling mode is enabled by setting the least significant bit in these registers, which I'm going to set to 0. So the only thing I need to set here is this part, so these bits, these 3 bits, which I've already calculated. Okay, so back inside the IDE, I added a comment on top of here just to make this more clear. So the first 4 bits is going to be this one, and that's going to be 0. So I'm just going to add a new define up here that sets this to 0. And I'm going to do the same for the last bit. And then, since this is the 4 most significant bits, I'm going to shift this 4 steps. And then this one, I only have to shift 1 bit. Use a plus here, doesn't really matter. And then finally, I could just remove these actually, since they are 0, but I will leave them here for clarity. And this is everything I need to do to configure the UART to a baud rate of... So quite simple actually, once you understand how you calculate the appropriate values to set the desired baud rate. And then let's try to compile this to see if it works. Well, there are a bunch of includes that I'm missing. That one. Okay, so now it compiles. I'm also going to add a comment on top here that just explains what I'm doing. So calculating the divisor, yeah, these are used to configure the desired baud rate. And whoever is interested in more information can have a look inside the user guide. And then I can move on to implement the function that's going to send a single character over the transmit line. And sending a single byte or a single character with this peripheral is really simple. You just write to single register and it will start the transmission automatically. So I write to this register here. And before I do so, I need to check if there is any ongoing transmission, which I can do by polling a register. So I'm polling the interrupt flag here, even if I'm not using interrupts right now, since the interrupt flag is set when the transmit buffer is empty and ready for a new transmission. And to make it more clear what I'm doing, I can just add a comment on top as well. And then one special thing that I'm going to do here, or a special character that I will be handling, is the line feed character. Because some terminals, for them to properly show a new line, they expect a line feed after a carriage return. So for that reason, every time I see a carriage return, I'm going to add a line feed as well. So first of all, I must wait for the previous transmission to finish. So if it's a carriage return, I just call this function again, but passing a line feed instead. And then a comment to explain why I'm doing this, like that. And then I'm going to call this function from within my main function. I will call this inside an endless while loop. And let's just use the character A, and I can print, yeah, maybe I do a couple of, and then I can add carriage return. And then to not print too fast, I can delay some cycles here. Let's see if this build, yeah, it did. Oh yeah, this should be a single, since this is character and not a, okay, so and then I have connected my UART peripheral, or the pins that the UART peripheral is connected to, with 2 jumper wires to my USB to UART bridge card, and then connected it to this USB port on my desktop computer. And then as a terminal program in Linux, I use the terminal program called Picocom. Not for any particular reason, really. There are a bunch of different terminal emulator programs that you can use. As long as you can pass the baud rate you're using, as well as any additional configuration for your peripheral, it's going to work. And when I plug this USB to serial bridge into my computer, it shows up as a device. So under dev/tty USB 0. And I can select the baud rate with the option -B. So since I'm using this baud rate, I'm setting this baud rate. I don't need to do any additional configuration to match the number of parity bits or stop bits, because Picocom is also using the same configuration as I set up for my UART peripheral by default. So this will just work as is. So then if I compile and flash this to my microcontroller, we should see some characters pop up in my terminal. We don't. Okay, so I ran into an issue here. It didn't work because I hadn't actually called the UART init function, so I hadn't initialized the peripheral, which I obviously have to do. So now if I run this, yeah, now it's working. Now my microcontroller The UART peripheral on my microcontroller is talking to my desktop computer, and it's writing artful over and over again. So that works. Of course, polling like this is not going to be a very efficient way to go about it, because for each character, if I print a bunch of character in row, so if I call this, if I, for example, want to print an entire string, I would have to call this function for every character, and for each character, it's going to have to wait for the current character to be sent. And this means I'm going to be wasting CPU cycles waiting for the transmission to finish, and while I could actually be doing something else, something useful. And that's why I'm going to improve on this in the next stage by replacing the polling here with interrupts. And the way that's going to work is that I'm going to have a ring buffer. So let's just say, for example's sake, that this is an array of size 8. So a ring buffer of size 8. 1, 2, 3, 8. And when I want to send a new character, I'm going to add the character to this ring buffer. So let's just say that I want to send the word artful again. So for the first character, I'm going to add this to the ring buffer. And if there is no ongoing transmission, then the UART will be in idle. So then I'm going to check, is there any transmission going on? And if it's not, I'm going to start TX by writing this character to the transmit buffer, just as I did in the polling example. So that's going to, well, in this case, it's going to write the character A, and that's going to start the transmission. And once I've done that, I'm going to return from the function that prints a character. So let's say I still have a function called put char, and it takes character C. So instead of writing A, I can write C here instead. So I add the character. So the first thing I do, I add the character to the ring buffer, and then I check if there is any ongoing transmission, and if there is not, I will start the transmission by adding this character to the transmit buffer. And then I can return from this function, and the CPU can go on and continue doing whatever it's supposed to be doing. So this means that the CPU will be executing, and the UART will also be executing. The peripheral will be executing separate from the UART, will be executing separate from the CPU. And then maybe the CPU does some execution, like it's going to take a little while, or it's not going to take a long while for the UART to transmit a single character, but the UART baud rate is much slower than the CPU clock rate, and this means that the CPU will have time to execute a few instructions before the UART has sent out the byte. So maybe the CPU executes some instructions, and then before the UART finish, it's going to try to put a new character. So maybe this time it's going to put R. And this is especially going to be the case if we have a function that prints an entire string, because then we're just going to have several calls to put char after each other. And this is also going to add the character to the ring buffer. And it's going to do the same check here. If no ongoing TX, it's going to start the transmission. But since there is an ongoing transmission right now, we are not going to go into this if condition here, so we're just going to return. And if the CPU is fast enough, it may execute the next UART put char. So that's going to be T. And then it's going to do the same thing as here. It's going to add a character to the ring buffer, but it's not going to start the transmission because there is already transmission ongoing. So then we have RT. Okay, so let's say that after the CPU has added the 3 first characters to the ring buffer, we get the interrupt. And as I explained in the last video where I talk about how interrupts work, when we get an interrupt, there is going to be a function that's going to be called, a function that we have defined, and a function that I'm going to define later on in this video. So it's going to call the interrupt function. And when we get into the interrupt function, we know that the oldest byte that we added to the ring buffer is the one that the UART has transmitted. And this means that what I'm going to do inside the interrupt function, the first thing I do inside the interrupt function is going to be to remove first from ring buff. So that's going to remove this character. And then if the ring buffer still has characters in it, if it's not empty, I will take the next character from the ring buffer and put it inside TX buffer to start the next transition. So now since I removed the first element from the ring buffer, taking the first element is going to give me another element here. So I removed the first element here, and then I take the next element, so that's going to be R. So I fill the transmit bit buffer with R, and that's going to start a new transmission. And then before I leave the interrupt function, I also have to clear the TX interrupt. And then we leave the interrupt function, and the UART continues transmitting the next byte, and the CPU continues doing whatever it is doing. So the CPU might be adding additional characters here, bam, 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 and the UART will eventually trigger the next interrupt and remove this character, trigger the next interrupt, remove this character, and so on. So, and let's just assume that this ring buffer is of size 8. So if the CPU continues writing characters to the terminal, it's going to fill up the ring buffer. So maybe B, Y. And since this is a ring buffer, or since I'm going to implement this as a ring buffer, when we reach the last position inside the underlying array, it's going to wrap around and start filling in characters from the start of the array. So B, Y, T, E, S. So it's going to go around like a ring, and that's why it's called a ring buffer. And the big advantage with this approach compared to the last approach is that there is no polling or blocking, and most of the time the CPU is going to be able to do something useful because it can just fill up the ring buffer and continue doing whatever it's doing, and then the UART can execute in parallel and transmitting the byte. Of course, the CPU is going to be interrupted when the transmission finishes, but this is a short interrupt function, so that's not going to take a long time. So overall, with this approach, we're going to be blocking less and wasting less CPU cycles. So let's now implement this in code.
To implement this, I'm going to start with the ring buffer implementation, and I will create 2 new files for that. A header file and an implementation file. And when implementing a ring buffer, you can get pretty sophisticated if you want, but I'm going to try to keep things as simple as I possibly can here. So first I will have a struct that defines the ring buffer data structure. And the first element in this struct is going to be the pointer to the underlying buffer. And then I will have a integer that holds the size of this buffer. And I'm making this variable 8-bit integer, so the buffer can't be bigger than 256 bytes, which is fine here. And then I'm going to have an integer to hold the head and an integer to hold the tail. So the head is going to point to the newest, or is going to hold the index to the newest element, and tail is going to hold the index to the oldest element inside the buffer. It's not super nice to define the entire struct inside the header like this, because the code that's going to be using the ring buffer, well, in this case the UART code, will have access to this entire struct, so it will know that inside this struct there is a head and a tail, which kind of breaks the coding principle of that the outside should only know what it needs about the inside. And then I'm going to have a couple of functions that operate on this ring buffer. So first I'm going to have a function that adds an element to the ring buffer. So in all of these functions I will be passing the ring buffer struct, or a pointer to the ring buffer struct, as the first argument. And then I have a function that can retrieve an element from the ring buffer. And then I have a function that gets the element from the ring buffer, but it doesn't remove the element from the ring buffer, so it's only peeking at the value. And as such, since I'm not going to change the ring buffer in this function, I'm going to pass that as a constant, or I'm going to pass it as a pointer to a constant ring buffer. And then I will have 2 functions that are going to check if the ring buffer is full or empty. Then we can jump over to the implementation file and implement the functions. So this function is going to insert an element into the ring buffer, and the way I'm going to do that is by setting the element that the head is currently pointing to, and then I need to increment the head so it points to the next slot in the underlying buffer. And then I must also check if the head is now larger than the underlying ring buffer, because then it has to wrap around and point to the first index instead. Alternatively, I could do it like this instead, so head equals RB head plus 1, and then, but as I mentioned before, doing modulo on my microcontroller is a bit expensive, so in this case I prefer doing it with an if condition here instead. So I'm also going to add a comment about that: avoid expensive modulo operation. And then as for the next function, I'm first going to get the element from the list. So that's going to be what the tail is pointing to. And similarly, I need to then increment the tail. And then similarly, I have to check if the tail is larger than the size of the internal buffer, or well, if it's equal to the size of the internal buffer. And I'm also going to add the same comment on top. And I have to return the data here. And the pick function is going to be simple, just a one-liner, returning the element that the tail is pointing to. These are also going to be one-liners. To check if the ring buffer is empty, I just need to check whether the tail and the head are equal, because at the beginning both the tail and the head are going to be 0. And then when you fill the buffer or the ring buffer, you increment the head. And once you start extracting elements from the list again, you start increasing the tail. And the ring buffer is empty when the tail becomes equal to the head, because then you have extracted all of the elements from the list. So I can simply just check if the head is equal to the tail in this function. Or the full is actually not going to be a one-liner, because here I need to also wrap around. So if the index after the head is the same as the tail, that means the ring buffer is full. So this is pretty much it for the implementation of the ring buffer. And then I can include this inside my UART file. And I can define this ring buffer statically by writing it like this. So first I'm going to have a separate define to name the size of the ring buffer that the UART driver is going to use. So I'm going to make this buffer 16 in size. I think that's more than enough, and it's probably bigger than it has to be. And then I can define the underlying buffer, and I'm making this static since it should only be accessible within this compilation unit. So this statically allocates the buffer, but since the elements in this buffer can change, it's going to be allocated in the RAM. And then I allocate the ring buffer struct, and I'm calling that tx buffer. So the buffer is going to point to the internal buffer above. And size, I can use the size of operation here. I could also just use UART buffer size, doesn't really matter, like this. I don't need to explicitly set the head and tail here, because they will be 0 initialized. So let's see if I can compile this now. I can't. Get an error. Oh yeah, I need to add some includes. Yeah, so now it compiles. And then I can go ahead with writing the code that's necessary for enabling or for making use of interrupts in this UART driver. So after I release the module for operation, I need to enable the transmit interrupt. And I also need to clear the interrupt before I enable it here, because after boot the interrupt flag will be set, since the interrupt flag is set every time the tx buffer becomes empty, and at boot it's empty, so the interrupt flag will be set. So if I don't clear it here, it will trigger an interrupt even though I haven't actually sent a byte yet. And I'm going to create a separate function for this. And then I also need to enable interrupts globally, this to work. There. And then I can go ahead and implement that function as well. It's going to be a static function, and I'm also going to inline this function since it's just going to be a one-liner. I want to avoid the function call overhead. And this is how you clear the transmit interrupt, by clearing this bit inside this register. Then I can go ahead and implement the interrupt function, the function that will trigger each time we have transmitted a byte, the function that's going to trigger each time a byte has been transmitted, so when the transmit buffer is empty. And by the way, the transmit buffer for this peripheral on my microcontroller is only 1 byte. There are other microcontrollers that will have a UART with a larger FIFO buffer, so maybe 8 or 16 bytes. And that's going to allow you to write several bytes to this FIFO buffer and only get an interrupt when all of those characters have been sent, which is going to reduce the number of interrupts you need to handle. Because in this case, I will need to handle an interrupt for each character. But that's just the way I have to do it, since my transmit buffer can only take a single byte. So the first thing I'm going to do in this function is to sanity check that the ring buffer is not empty, because for this implementation, each time I'm going to send a new character, I'm going to add it to the ring buffer, and then I'm going to remove it from the ring buffer once it has been transmitted. So I'm going to remove it inside the interrupt function. So if I ever get to inside the interrupt function and there is no element inside the ring buffer, that means that I have got an unexpected interrupt. So I should assert here. Well, I will leave it to do for asserting here, because I'm not sure I want to use the current assert implementation that I have inside an interrupt function. So for now I will just do a while loop so it's easy to spot. And then I'm going to call the ring buffer get function to remove the element that was just sent from the ring buffer. And I don't need to assign the return value to a variable since I'm not interested in the value. I just want to remove it from the ring buffer. And then I need to clear the interrupt, because on the MSP430 interrupts are not clear automatically. You have to explicitly clear them inside the code, because if I don't clear this here, this interrupt function is going to keep on triggering even though it hasn't sent any new bytes. And then at last I'm going to check if there are any remaining elements in the ring buffer. And if there are, I'm going to start a new transmission. And note, I'm clearing the interrupt before I do this, because I want the interrupt to be cleared when the new transmission starts. But otherwise, theoretically, if I clear the interrupt here, it's possible that the transmission I start here, that I clear the interrupt for when this transmission finishes. That's likely not going to be the case, because this is going to execute much faster than the UART will be able to send out the byte. But it seems, or it feels more correct to clear the interrupt here. Okay, and then I can implement a function that's going to start the transmission. And here I'm also going to make sure that the ring buffer is not empty. And if it's not, it means there is an element in the list that we should send. So then I'm going to do similar to what I did in this function. I'm just going to write to this buffer, the character to this buffer. So here I'm going to use the peak function. And I'm using the peak function here because I just want to get the element when I start the transmission and put that inside the transmit buffer. And then once the transmission is done, I get the interrupt. And here's where I remove the element from the ring buffer. So what you can see from this is that if I have a bunch of characters inside the ring buffer, the interrupt is going to keep on driving the transmission until all of the characters have been sent. And then I need to implement a function that puts the character we want to send into the ring buffer. So I will have a function here called UART putchar interrupt. So here I'm going to add the character that was passed to the ring buffer. And I also need to check if there is any ongoing transmission, because if there is no ongoing transmission, then I have to start it here in this function. And if there is an ongoing transmission, that means that I don't need to start it here, because the interrupt will keep on driving it until the ring buffer is empty. And then it's enough to just add element to the ring buffer. And to know if it's ongoing, I can just check whether the buffer is empty or not. So if it's not empty, it means the transmission is ongoing. And then if it's not ongoing, I need to start it. And then I just call your tx start. And then to make this safe, so that I can safely access the tx buffer here, because there is always a risk that I will get interrupted somewhere in between these lines of code here. I'm going to disable the interrupt before and after, so that the interrupt can't occur while I'm executing this portion of the code. And then, same as before, I'm going to handle the carriage return. And I also need to define these functions. I will move to use this function here as well, be enable tx interrupt. Then I can call that here. And also disabling the interrupt. And then one last thing I'm going to do in this function is to make sure that at the top I block here if the ring buffer is full. Because if it's full here, it means that we have put so many characters in the ring buffer and the interrupt-driven transmission has not been able to send out the bytes as fast as we have been able to add new bytes to the ring buffer. So in that case, I'm still going to be polling. But I actually tried this function and really stressed it, running this microcontroller at 16 megahertz and calling this function over and over again on long strings. And I have never reached a point where the ring buffer is full, but it feels better to have this while loop here anyway. So if there ever is a case where the ring buffer fills up, I'm not going to end up overwriting old values. I'm just going to poll here for a bit instead. And then I need to make sure that I declare this function inside my header. I can check to see if it builds. It did. Good. Can we replace this with the interrupt function instead? And then we can open PicoCom and run this. Well, I have to connect my launchpad again. So I had some issues here, but now it seems to be working.
Yeah, so the interrupt driven function also works. I can also add a temporary print function here that takes a pointer to an entire string. And I'm just going to loop over the string until I reach the null termination. And then I can just call the putchar interrupt and increment here. I need to do it like this. So for this to work safely, it's important that the string I pass here is actually null terminated, but this is just a test function, so this is fine for now. Then instead of doing this, I can instead write like this. Oops. Now if I compile and run this, we should see artful bytes over and over again. Yeah, and we do. Good. And then in the next video, my plan is to make this print function work more like the standard library printf function, where you can pass also pass integers and so on as part of the string. So this year and then something like that, which I can't do with this function now, but that's for the next video. I'm also going to add a few more comments to my ring buffer implementation here, since the way it's implemented right now, I don't have any checks inside this function to see, like for example when I call get, I have no sanity check or assert to check if the ring buffer is empty. So I'm just going to have a comment here that says that caller must call is empty first. So I could of course have a search inside this function, but that's going to add additional code that needs to be executed each time these are called, and I would like to avoid that in this case. Another thing I can mention is that I could possibly put this inside like a define macro, so that the only thing I need to write is something like ring buffer and then the name of the buffer and like the size. But I think since I'm not going to have that many ring buffers in this code, it's just going to be nicer to write it explicitly like this, because macros can sometimes make the code harder to understand. So now that the interrupt-driven solution works, I'm just going to move this code over to my main project. Okay, so now I moved all my code to my main project, so moved the two UART files as well as the ring buffer code. And I added a test function to test.c that basically does what I did in the IDE. So it prints this string and then waits for 100 milliseconds. I did notice an issue in my code here that prevented this from working. Inside MCU init, I set these, like the clock rate like this, and that doesn't actually work. So I made an error in the last video, and I don't fully understand why it still worked in the last video when I modified my busywait macro, but for some reason it did. But I will add a comment under that video to point out this. So after I changed it to like this, then it works. And I also added a new assert here, assert interrupt, which is an assert that can be called inside an assert function, which I do in the transmit assert for the UART. I haven't actually decided what I'm going to do in this interrupt yet, so for now I'm just having an endless while loop here. Other than that, there's not much to say. I obviously added the new files to my make file as well, the ring buffer and the UART. And I don't need to configure the IO pins like I did in the IDE, since that's already done inside io.c. Here is where I set those. Yeah, so then I can go ahead and commit this code. First I'm just going to fetch the main, and then I'm going to stash this and git checkout main, and then stash pop and create a new branch. So this is going to be a feature UART driver. Then I can format my code, CVP check, or I build all of the test functions. Yeah, and that works. Then I can add all of the existing files and also add the new files. And then commit. There we go. And we can push this change to GitHub. Open a pull request. And while the CI is running, we can just quickly look through the code to see if there is any mistakes. It's annoying that formatting does this, puts the semicolon on a new line. I should use braces here instead, but I'm not going to fix that now. And this to do I'm going to handle in the next video. Yeah, so overall I think this looks good. Yeah, and the checks passed, so now I can merge the pull request. So that was all for today. See you in the next video.